I want to introduce you to ESASky now and how you can actually use it for your science. So this presentation is on behalf of the whole ESASky team, in particular Fabrizio Giordano, who is the senior software engineer of the team, Elena Acero, who is a software engineer and scientist, Henrik Norman, Matthias Wangblad, and Thomas Fozzi, who are all software engineers working on ESASky, Marcos Lopez Caniego and Elena Puga, who are both archive scientists contributing to ESASky, Bruno Merin, who is the head of the ESA Science Data Center, Elena Colomo, who is our ESDC Astronomy Archives technical lead, and finally Guido De Marchi, who is the ESDC Science lead. And my take-home message of this talk is that there are many hidden jewels in the archives, as we know, but ESASky is your tool to find them. So ESASky is a multi-wavelength and multi-mission portal with access to data from more than 60 space-based and ground-based missions, and it facilitates data discovery, archival science, and even unplanned science. And I'm hopefully going to convince you and recruit you to try out the tool, if you haven't done so already, in the next 40 minutes or so. So this is the overview of my talk today. I'm going to give you a quick introduction. Then I'll show you some recent scientific papers that have used ESASky. Then I'm going to demo the tool, show a few slides with statistics and how the ESA mission data is being accessed by the users, and then tell you about our exciting future plans and finish with a summary. So we've been developing ESASky over the past more than 6 years, and it has turned into a platform and a suite of tools for scientists driven by scientific use cases and the needs from the scientific community. So we have the main ESASky interface, which is at sky.esa.int. You can open this up using any browser on your PC, in a tablet, or even from your mobile phone. Then over the past 6 months, ESASky is also becoming an ESA legacy archive. And I refer you to the tech talk that was given by Elena Puga at the end of January about the repatriation of Hipparcos data to ESA. So currently this legacy archive contains Hipparcos and COS-B tables and data. And then we have programmatic access via a number of different ways. So we have a widget called ESASky that has been developed to work in Jupyter notebooks, where you can perform additional scientific use cases that you can't do in the main interface. And I'll quickly show you this in a demo as well. We also have an AstroQuery module, and we have table access protocol, a TAP, for those of you that know about these things and how to use them. So you can use any of those tools to create scripts or Jupyter notebooks that are then reproducible and can be shared with collaborators. And then finally, just to mention, but I won't go into any more detail, we have a JavaScript API, so an application programming interface that can be used to embed ESASky into a web page or a web application. And a number of archives are interested in using this. You might see ESASky in the future in the archives as one of the visualizations. So how do we obtain the use cases and feedback from the scientific community? Well, we have a help desk and we have a user echo forum where we get a lot of feedback and suggestions, and many of you have contributed to this, so many thanks. We have an Astronomy Archives user group that consists of 8 scientists from the community, and they are our official body advising ESA. They provide us with recommendations on the future development of the Astronomy Archives, and in particular on ESASky and how to improve ESASky as a tool for scientists. We run user surveys, and the last one we had 2 years ago had questions about ESASky. and more than 2/3 of users said they use ESASky for science, which is great. We also engage with the community at conferences. Obviously, this hasn't been face-to-face this past year, but we have been running archive lunch sessions at the European Astronomy Society annual meeting. And we've got our third one coming up on Friday, the 2nd of July. So if you're able to join us then, please do. This will be run by Guido. And then we also perform usability tests. So these not only help us improve the design and general usability of the tool, but they also lead to very useful conversations on how the tool can be improved for science. And we're always interested in running more sessions, so do contact us if you're interested in volunteering. Now I want to show you a couple of recent papers by the community that not only have acknowledged ESASky, but they've briefly explained how they use the tool. So the first one is by Peter McGill et al. On the predictions of Gaia microlensing events. And they analysed the microlensing events predicted from Gaia DR2 and created a diagnostic test for spurious microlensing candidates, whilst also improving the reliability of these predictions. So over here, we have one of the figures from the papers showing the G magnitude versus one of the astrometric errors. The red sources are the spurious sources with the large errors. The green sources are the more well-behaved microlensing candidates. And in the paper, they estimate how many events will be observed by Gaia and suggest that at least half of the astrometric microlensing events during the Gaia extended mission period are yet to be identified. So just to remind you what microlensing is, if I can start this, start this little video as well. So this occurs when a massive object called the lens aligns closely with a distant background source, and two images of the source are formed, resulting in apparent brightening of the source and apparent deflection of its position, which is the astrometric microlensing. And it's possible to predict these events when all the astrometric parameters are known. For both the source and the lens stars, hence why there were so many predictions made with the Gaia DR2 data. The authors used ESASky to inspect images in the optical from the Digitized Sky Survey and the Sloan Digitized Sky Survey, in the near infrared from the 2 micron Sky Survey, and in the mid-infrared from the All-WISE, the All-Sky release of NASA's Wide Field Infrared Survey Explorer. And they use these to determine whether an event is plausible. Over here on the left, we see a figure from the paper where you can clearly see in the optical on the left-hand side and in the near-infrared that you don't actually see the source. So the source is the blue circle. And to the right, here's an example in ESASky of a nearby lens star that's creating many, many microlensing events. Here's another example paper. So it's a short one, but it's a typical archival research example where the authors discovered a serendipitous observation of a tidally disturbed galaxy pair whilst actually exploring data on a different target. And they investigate other archival data, including spectra from the 6 degree field galaxy survey. And they use ESASky to continue data mining, and they find that there are also XMM-OM, the optical monitor instrument on board XMM. There are observations from this. And then the third example is a paper by Elena Racero. She works, as I said earlier, within the archives team and the ESASky team. And this has been a great collaboration with scientists in the community and with scientists and some software engineers at ESAC in various missions and in the ESDC. And the paper is twofold. So it describes a solar system object service, and it also illustrates the specific case of serendipitous observations in Herschel of the asteroid Psyche. And this is exciting because there is a NASA mission to this asteroid due to launch next August. So describing first the pipeline, this was created by Elena and Fabrizio using software from the Institute of Celestial Mechanics and Ephemeris Calculations, in collaboration with Jérôme Berthier and Benoit Carry. Some of you might remember Benoit was a research fellow at ESAC. And the pipeline takes the satellite spacecraft kernels, so the position of the spacecraft, to then compute the orbit of the asteroids as seen by each spacecraft. And then it performs a geometrical cross-match against the mission imaging footprints and the start and end times of the observations to see if the object falls in any images. And the pipeline's been run against more than 800,000 asteroids and 2,000 comets. This is available in ESASky. And we have this available for 3 missions: XMM Newton, Hubble and Herschel. And in the paper, we also report on the XMM OM instrument. The results are a catalogue with a complete list of potential detections of asteroids within estimated limiting magnitude or flux limits in the images. These include more than 900 serendipitous detections in Herschel and XMM-OM, and more than 32,000 potential serendipitous detections in the Hubble images. And these initial images were used in the Hubble Asteroid Hunter Citizen Science Project, as described by Sandor in his seminar talk on the 4th of March. And in the image, you can see an example of a serendipitous observation of an asteroid in a Hubble ACS image. And then the thermal properties of Psyche are also investigated in the paper using the 4 serendipitous Herschel detections. So the thermal inertia is calculated, which is a diagnostic parameter for determining if the asteroid has a more metallic or silicate composition. And the conclusions are that it's more consistent with silicate powder than with a metallic surface. Also, looking at the emissivity, the conclusion is that it may well favour a high silicate content, but the authors do stress that more thermal measurements are needed. And this is interesting because the NASA Psyche mission aims to journey to a metal asteroid, and it could well be that the Psyche asteroid has more silicate composition than they would want. So we'll see next year. So let me go to my demo. I am going to share now my screen, and I'm going to take you to ESASky. Let me get some water. So when you load ESASky, this is what you see. You have a welcome box. You can choose 2 different modes. I'm going to show you the functionalities in the science mode. And here you have the whole sky available for you to search and explore, so you can zoom in, zoom out, pan around. Over here we have the search button, so you can search for any astronomical object, you can search for solar system objects, you can input coordinates. You can also search by author and bib code for any associated sources associated to publications per author or per paper. Now, let me go, I'm going to go and go to an object that was in the first science case example that I showed you. So we're looking in the optical, in the Digitised Sky survey. This is one of the lens objects in this paper, so it's very fast moving nearby star. And the blue, so this is the same object, it's just that the blue and the red images were taken probably about a decade apart even in this region of the sky. And the authors loaded up, they compared the optical, the near infrared and the mid infrared. So we can do this by coming over here. These are all the buttons over on the left for the scientific functionalities. So we have the first, if you want to change the sky background, you select this first button, and I'm going to also load up the near infrared. So here we have the 2 mass and mid infrared, so all Y's, and you can actually start playing through these skies, or you can grab the scroller and play through. So you can see already how fast moving this object is. So these images were taken in about 2000 or Y's in about 2010. So you can see how many sources that this star's already been transiting and creating microlensing events. We have the next buttons here are all for accessing data from the archives. So we have images, catalogues, spectra. These numbers are telling you roughly how many images or sources are available in the field of view. So let's open up the catalogues, and you're shown a tree map. So the larger the box, the more sources there are in the sky. You can also filter this by wavelengths if you're only interested in the high energy catalogues, for example. You can filter. So I've loaded up the Gaia sources, which is what they would have done in the paper as well. And you immediately see that there's a solid arrow here for this source. So this is this high proper motion star that we're looking at. And the arrow goes from the epoch 2000 to the Gaia EDR3 epoch, so that's 2016. Let's also open up the 2 mass catalogue. The yellow is a little bit difficult to see, so it's very easy to change colours, change shapes as well of the catalogue sources. And we can play through the skies again. So you can clearly see that many of these stars have already been microlensed, and many of these ones down here will be creating microlensing events during the lifetime of Gaia. Now, if I want to, let's say, open up images in this region, then we just click on the imaging button. You see another tree map. It's very, very similar to before. So everything's interactive on the sky and in the data panel. You can also filter all of the columns. So when I filter, you saw that maybe here, it filtered out all the HLA collection. So if I clear that, then everything else appears in the sky. Let's load up the other and zoom out. So we see these are the footprints. The XMM footprints are a lot larger. And we have direct access to the archives. Firstly, here from the preview column, if I click here, then we open up a postcard. This is coming directly from the XMM archive. And if I click on here, then I open up the XM Newton Science Archive for that observation. You can see how fast this is. And it's also very easy to download the data. So you can download the metadata here, or you can download the data products. So just a few clicks of the button. And we have this is new, we have a settings button. So if there are more columns available, then you can load them up to visualize them. And when you download the metadata, you're downloading everything. So this is really useful for catalogs such as Gaia, for example, that have many, many columns. So you can see them all here. And when you download, as I said, you download all columns by default. It's also identical with the spectra. So I've clicked on the spectra button and you can start to load up your spectra. So here we have some IUE spectra. We're linking to the archive, and this isn't an archive at ESA, so this is going straight to the INES IUE archive at CAB. And then the final button for accessing data is this one here. So it's to access all of the external data centers in the region. And we have data from the European Southern Observatory, from the Canadian Astronomy Data Centre, and from MAST, which is the data centre in Baltimore. Let's change scenery and just go to another object. And I'll clear these. So I can start loading up some data directly from ESO. So I'm getting this metadata. It hasn't been curated by us in the ESASky team at all. It's just coming directly from ESO. And you can download as well very easily. So in the case of ESO, you have a list, and normally the science file is the top one. Let's open it in DS9, for example. And while I'm doing that, I could load up some others. So we have cubes and time series. We have other types of data from these data centers. So we can load them all up from across the Atlantic. Let me close this and show you the next button. So this is the publications button. And when I click on here, you see a lot of these icons appearing on the sky. So this is every source that has an associated publication. And you can select an object, for example. Let's see, and I get all the data here. Just going to minimize ever so slightly. So these are all the papers associated to this source. Now, it's CDS, it's the data center at Strasbourg that have done all this work. They have linked objects to papers, and then they're providing a service, and we are just linking to their service. So we have access to all the papers. We have access to each individual paper at NASA ADS, and you can also load up the sources associated to each paper. So here we go. These are the sources for the first paper that I've selected here from this parchment button, and you can click through them and investigate them. And the next button to show you it's already selected is this target list button. So there are a list of predetermined target lists that you can take a look at, or you can upload your own target list. This is the typical format. It's very simple. It can just be names of targets or coordinates, and if you want to add a description, you can do. So I load this up, and here we see all the targets, and here's the description that I added. So the final button to show you is this one here, which is the planning tool. Currently this is for the James Webb, so I can open here, select any of the 5 instruments on Webb, and when I choose one, so I've chosen NIRSpec, you see the footprint of NIRSpec appearing on the sky of the instrument. You can choose the aperture, and you see that changing in the sky. You can select all instruments in the focal plane as well, so you can see if you want to do parallel observations, for example. And you can change RA deck, move around, change the position angle. You can change it. I heard a question. Is that a question from someone? If not, we'll carry on. And then once you're ready, once you have an idea of how you want to do your proposal, you copy the coordinates and data, and then you copy this into the official astronomers proposal tool of James Webb and carry on with your proposal there. So the last thing I want to show you is, let's close this, is searching for solar system objects. So let's go to, let's search for the Psyche object that I showed you earlier, talked about earlier. So you're told that there's an asteroid called Psyche. There are Herschel observations available. This line, if I zoom out, this is the orbit of the asteroid as seen by Herschel over its entire lifetime. And you can go to the observations by clicking on this button down here, zoom in, and you see there are 2 Pax and 2 Spire observations, and the target wasn't Psyche, the target was this dark cloud nebula. And then if I change the background, let's go and open up the Herschel Pax background. So this was created in this region of the sky with these 2 Pax images. So what you see when you zoom in, and perfectly aligned with the predicted orbit, you actually see the 2 images of the Psyche asteroid. And you can even see this in the postcards coming straight from the Herschel archive. So there are a lot of serendipitous objects just waiting to be found in ESASky. So please enjoy exploring. Now, I am now going to move over and show you ESASky. So let's say you've done a lot of work in ESASky and you want to redo it tomorrow, but maybe you haven't written down all the steps you did, so can't quite remember. So the great thing about notebooks is that you can reproduce them all the time, and of course you can share this with your collaborators. So this is a quick demo of a short notebook. So I'm in Jupyter Lab here. So I've already run a few of the Python modules and run ESASky. And in Jupyter Lab, you can actually view ESASky of the output view over here. So this is interactive. This is like having ESASky in your browser as well. You can do things here if you want to, but of course, with the notebook, we want to do things by the command line. So I can go to an object. I'm just running this cell over here on the right-hand side. We can change the field of view, for example. We can change the background skies. So we're now looking in the XMM Newton epic color. If I want to get data, it's very simple. So first of all, I'm plotting the XMM Newton serendipitous source catalogue up in this region of the sky. Then I'm getting the data into the notebook, and I'm going to do the same for one of the Herschel-Pax point source catalogues and get it into the notebook. And you can do this with all of the imaging data and spectra and all the data from the external data centers. So here's an example for the Chandra imaging, and you can even inspect the data here in the notebook. So here's one of the Chandra postcards. Many people ask us if you can do cross-matching in ESASky, which you can't do on the interface currently. But of course, you can do that in a notebook. So here's just an example of a cross-matching using AstroPy libraries. So we're just doing a simple positional cross-match with the two catalogues that we loaded up. And then you just send this catalogue here with a few clicks. You can send it. So this is the catalogue in yellow now, cross-matched in the sky. And another request we get is if you can view catalogues from Visio. So this is one method in the notebook. So you can use the AstroQuery Visio module. I'm querying AstroQuery to get the Verum Ceti catalogue in this region. And then I just send it again to ESASky. So that's these blue cyan sources that you see here. So you can also upload your own tables. You can upload your own data and send them to ESASky. And there are many more things that can be done. And we've got example notebooks in GitHub if you want to know more, and do contact us if you want to know more. So let me go back to my presentation and start this up. Great, so I just want to spend a few more minutes and firstly to show you some statistics on the usage of the tool and how the users are accessing ESA mission data. So this shows the number of users of ESASky since we first released in May 2016 up until last month. So you see there are lots of peaks, and then there is we've had over the past year, we've had a lot more users per month, a lot more visits per month. So the reasons for these, well, a lot of the peaks initially were announcements of the Gaia DR2 release was very large as well. But the increase in users since March 2020 is due to a number of reasons. So obviously the lockdowns happened in Europe in March 2020, and ESA Communications started advertising home activities for school children, which included ESASky. And we also released ESASky early on in March with ALMA data, and we advertised this widely. And then over the next 3 months, ESA Communications carried on advertising ESASky via various social media platforms during the European lockdown period. And then in June, we released ESASky in Chinese. And this was also advertised in China and with an ESA SciTech article. So since then, we're really seeing a steady number of visits per month. So it's around 5,000. We also record events. So this is we've been using Google Analytics, and we replaced it with Matomo so that we're compliant with EU data protection laws. So these events help us to prioritize development based on user usage, and they include accesses to the archives and the downloading of the data, how often the skies are visualized, how often postcards from the archives are visualized, and even how often particular buttons are selected. So here are the statistics on the visualization of the ESA mission skies, or HIPS. So HIPS is International Virtual Observatory Alliance protocol that we're using. And you can see that Exmouth Newton, Herschel, Hubble and the Planck skies are the most viewed skies from the ESA missions, and they're viewed thousands of times per month. You can also see that there's we're seeing a steady increase as well. And here's another example. So these are the opening of an archive postcard. So in this case, the Hubble postcards are clearly the most opened, with quite a few hundred opened per month. And from these statistics and others that we have on accessing the archives, we really do see that ESASky is exposing users to the ESA mission data, and it's helping to direct users to the ESA archives and any other archives that we have in ESASky. So our future plans, so we have a long-term vision to link to all major astronomical data centers worldwide. And this helps enable science, the more data that you have. So we want to add more data for ESA missions in operations, ESA missions in legacy, add more external data centers. We're almost ready with Astron, and we're almost ready with some of the data from ESARC. We want to allow users to upload their own data. That's very important as well. We want to show future planned observations for missions in operations, and to add more missions to the planning tool would be great. And then on the technology side, we're working on the API to be released in public versions of the archives. We're updating constantly the AstroQuery module, ESASky, and of course we want to link to ESA Data Labs in the near future. Here, this GIF's showing you an example of something that's in our development version now. So it's a request from one of the missions and also the users group, and that's the selection in the sky of either box or circle, so like a cone search or a polygon. So that'll be available very soon. We're working on a new viewer. We want to add more advanced visualization of data, such as images, spectra, time series, cubes. We want to update the solar system object pipeline, the service that I told you about. For those of you that heard me talk many times, we keep saying we want to add the time domain search, so that's going to be added very soon. And we want to add user areas, so users can save what they've done, essentially. And there are many more ideas. So the creation of the tool isn't possible without collaboration, especially with other data centers. So we are using Aladdin Light as the visualization tool from CDS in Strasbourg. And of course, we're linking to other services from CDS as well. We use astronomical data standards by the International Virtual Observatory Alliance. And this has made both the creation of the tool and the sharing of data with other data centers far easier, since we're all using the same standards. And then we've been collaborating with many different teams, including the AstroPy, AstroQuery teams, to develop the AstroQuery module to ESASky. So this is the list. These are all the people and institutes that we've collaborated with so far. And we really welcome contributions from anyone who's interested. Here are a number of links for you for reference, for if you're looking back again at this presentation and want to know more. And then this is my summary slide. And I hope I've shown you that ESASky is a suite of tools developed for scientists to facilitate data discovery and archival science. As I said, the vision is to link to all major astronomical data centres and to help enable science that couldn't happen before when you didn't have access to so much data in the one place. The Astronomy Archives user group has played a very important role in improving ESASky for scientists and the uptake in the use of the tool by scientists. ESASky is losing many users to the ESA mission data and mission archives. As I just said, the access to data and ease of adding new missions is all thanks to IVOA protocols and to the international collaboration that we have between the astronomical data centres. And if you use ESASky or PyESASky for your science, then please do acknowledge us. That's really useful for us to be acknowledged. So we'd especially like to thank all of the ESA astronomy mission SOCs or who've been involved, all of the ESA communications people at ESAC and ESTEC, and of course the Astronomy Archives user group. So many thanks.
Thank you. Thank you, Deborah.
Thanks.